go. All right. So astronomical unit is, remember I talked about astronomical unit and the, let's see, which one do I hit? This one? Yeah. Astronomical unit and a light year. Okay, those were two on a slide. Astronomical unit is much shorter. And AU just looks at our solar system. It's the average distance between the Earth and the Sun. A light year is a lot bigger. A light year, I kind of do that picture of the little person and the star. Mm-hmm. Okay, so basically light from that star, which is kind of blue, okay, it takes 1 year to travel if that star is 1 light year away. That's how that works. So it's kind of using light year. Light year is a distance. Looking at distant galaxies, the relative age. Bless you. This is an example where I don't know if you'll be able to kind of see this little picture, but you probably recognize it from your textbook. This is where you have an observatory, and it's looking at two galaxies. One is closer and one is farther away. Okay. So the closer one is younger, and the farther one away is older. Okay, that's kind of the gist of that. Cosmological horizon is kind of the edge of the observable universe, and it bumps up at a distance that is pushing how old our universe is. So about 13.6 or 14 billion light years. The next one, key dates and times on a calendar, cosmic calendar. So I don't know if you recognize those two things I pulled in from your lecture up there. You know, if we go January 1st, right at midnight is the Big Bang. And then we go clear to December 31st, almost right to New Year's is now. Okay, this is kind of how the things fall into place. Okay, in February, I'll go ahead and narrow it down. I can't remember which one's for sure. I might be missing one, but I do know there's one about the dinosaurs. I just thought that was neat. Okay, so for instance, you know, December 26th on the cosmic calendar, you know, the dinosaurs were here, and then was it 4 days later they died? Okay, and that's December 30th. Okay, so if you're like me, this is the sort of thing I would put on my note card. Let's see, the next term is time it takes Sun to orbit the Milky Way. That actually is just a number. 230 million years is when the Sun orbits the center of our galaxy. What is what stuff? Oh, the stuff at the, yeah, that's the cosmic calendar. Do you want to come closer, Nellie?
It's in your book.
Yeah,
okay.
it is.
What is?
They're just screenshots, yeah.
I was really behind. I'm sorry.
Howard foreign.
So that's that. The time it takes the Sun to orbit the Milky Way is pretty straightforward. Where is most of our Sun's mass located, and how is that determined? So we'll be talking more about this, but what you're looking at in this little picture is kind of like looking at the galaxy edge on, and most of the mass is actually in the halo region. So see, I have the galaxy, and I have halo and halo. That's where most of the mass is. Okay, most of the mass is outside of the disk. And how was it determined? It was determined by observing the motion of stars. So for you guys in here, will you, if I put something up, will you be able to download a PDF that has this? Okay, good. Because I would if I was a student. Will you be able to visit the website, the course website, and get this? A printout?
I should be able to.
Okay, I think so. Okay, the next one, raisin bread and expanding universe. Of course, there's your raisin bread. And in this case, the raisins are actually clusters of galaxies that are all moving away from each other. And then over here in green, I say the further away the galaxy is, the faster it's moving from us. And then I have a little heart around the raisin that's called the local raisin, because of course we're called the local cluster. Wasn't that so adorable?
So you're going to be like downloading like this exact slide with like all the
This exact slides with all this writing on there. Yep. Galactic recycling looks like this, where basically galactic recycling is a little star within a galaxy far, far away. No, actually, in our galaxy, we have galactic recycling too, where a star lives its life and then it dies and it gives its stuff up for new stars to be born. But honestly, as it lives its life, it's making heavier and heavier elements, which is important. And
Isn't that heaven?
heavier
Heavier
elements.
elements?
Heavier elements for new stars to be born. And then the ecliptic plane is, like we talked about tonight, this is a figure from your textbook where kind of the blue sheet there is the ecliptic plane, because the blue sheet there goes through the sun and it also goes through the Earth's orbit. And all the planets are kind of on that too. And then the last one, actually the last one I know is a short answer question on your test. Remember, what's that?
So that's what they're gonna be.
What are we going to
The
ask?
ecliptic plane again.
The ecliptic plane, yeah.
Is, plane. Re-say what you just said about that.
The ecliptic plane?
Uh-huh.
The ecliptic plane is kind of the blue area, kind of looks like a sheet of paper.
Uh-huh.
In the middle of the sheet of paper is the sun. And notice like the ecliptic plane is kind of in the middle of, goes through the middle of the sun and the middle of the earth. So basically all kind of float around on the ecliptic plane. Not float, but move within the ecliptic plane.
So the ecliptic plane's got the 23.5 degrees where the Earth is.
Well, it's kind of got,
It's got a degree too.
well, we usually kind of say the ecliptic plane is flat.
Okay.
Yeah.
Then I got that right on my paper.
Okay, you did get it right?
Then I got that right on my paper.
Okay, very good.
Okay. I want to get it right on the test though.
Very good. You got it, you're right.
I didn't say anything.
So, because I said,
I
okay,
acted like I was gonna throw my pen at you.
the ecliptic
said
plane is
cold-blooded,
like flat,
not
stationary
Mm-hmm.
plane, and then the axis is like the Earth's axis tilt is what the 23.5 degrees, and to me is what it sets on. It would, you know, pretty much like it sets on, kind of stationary on the plane, so it would, you know.
I think so. I think so, yeah. I think you got it.
Okay.
You
Okay.
said that one was gonna be a short answer or the next one?
This last one over here is going to be a short answer. Are we ever setting still? So like there, we kind of had a. I know it's hard to see, but of course we're spinning on our axis. So I think I'm going to have you come up with 3 ways. Why are we not sitting still? And one of you could just say we're rotating, okay? Which we said if you're at the poles, you're not really rotating. You know what I mean? But you're rotating, and we're orbiting the sun. That's 2. And our sun is moving within the Milky Way galaxy, that's 3. And our sun is also kind of bobbing up and down, I think that's 4. And then within the Milky Way galaxy. And our galaxy is kind of moving within our fellow galaxies. And then then the Big Bang, or the expanding universe is also giving us motion, so that's 6. Yeah, exactly. Okay, on to chapter 2. Circumpolar stars are stars that never set below the horizon. Polaris, NCP stands for North Celestial Pole. That's our pole star, North Celestial Pole, Polaris. And Earth's North Pole is pointed at Polaris. And then I also have with Polaris that the stars, it's so important because the stars are going to go counterclockwise around Polaris. I brought in a picture for the next one, locating Polaris using the Big Dipper. Okay, so that black thing up there is a figure from your textbook that says, you find the Big Dipper, you use the 2 far bowl stars, and then you kind of go up in a line and you find Polaris. Okay, the next one is if you find Polaris, then you can use the altitude of Polaris to know your latitude. Altitude, latitude, they sound so similar. So the altitude with the horizon gives you your latitude on Earth. I can't spell latitude. Seasons, why they occur, the basic reason is because the Earth's axis of rotation is tilted. Okay, and the two big things is, since it's tilted, the number of daylight hours we receive by latitude varies throughout the year, and the directness, that's supposed to be changing directness of the sun too. Hey, Brian. Then why we only see one side of the moon, that's that synchronous rotation. So I brought in that figure from your textbook where the guy is spinning on his axis as he orbits the sun, and you see the same face. See that little moon, two moons next to each other? That was the figure I was trying to bring in tonight. So the left one is the near side of the moon. The right one is kind of more cratered. That's actually the far side of the moon. I couldn't bring in tonight. So we only see one side because of synchronous rotation. Terminator, I bet you're okay with that. It's the division between the illuminated and non-illuminated part of the moon. Lunar and solar eclipses. Okay, I kind of had a little bit to say about each one of those. A lunar eclipse can only happen during full moon phase. And we say, in purple there it says, we say that the moon passes into the Earth's shadow. In orange there, that's the solar eclipse. Solar eclipses can only happen during the new moon phase. In that case, the Earth passes into the moon shadow. And then in green there, for that same line, I said umbra is the dark part of the shadow, and penumbra is the light part of the shadow. Oh, let's see. I think I blew off types. I have to add that. So precession, I'll come back to types here in a minute, of eclipses. So precession is basically the Earth's axis of rotation stays tilted, but it kind of cones like a top. And that's where Polaris is our pole star now, but Vega would be our pole star like in 13,000 years, I think. Okay. Hypothesis. This might be in the wrong chapter, because we just talked about that in chapter 3. Hypothesis is part of the scientific method, and hypothesis is a proposed explanation based upon observations. The last two go together, zenith and local sky. Zenith is right above your head, okay, and your local sky. Within your local sky, your altitude was what we've been talking about, where you can kind of use your fists to kind of see what the angle is of something in the sky. So I need to go back to types of eclipses, and I'm going to have to add this. I've got room on here to add it, but I don't want to add it and mess up my slide. So types of lunar eclipses. This one. Oh, pretty dark. Okay, we talked about total. This is types of lunar eclipses. Total lunar eclipse, and that's when it goes through the umbra. That one is really good, remember? And then partial, where at least you get a bite out of the moon. So at least, I'm going to say part of umbra. And that one's pretty good. The whole bite thing, yeah, it's pretty good. And then we have a penumbral eclipse. Lunar eclipse, don't even bother. I have before. I've always been disappointed. Penumbral eclipse. I will add it to this slide when I post it. Okay, and that is, it just goes through a penumbral part of the shadow, and it's no fun. Penumbral shadow, I'll say. Okay, those were lunar eclipses. Solar eclipses. Okay, kind of fall into this. Total solar eclipse is awesome. you'll see the sun entirely go away. Let's just put total eclipse is great. Actually, even a partial is great. You'll see a bite taken out. Actually, I say a partial is only great if you have a telescope. I'll put telescope here. Because you'll see a bite taken out of it. And then the other one is annular eclipse, and yes, you will also need a telescope to enjoy that. The annular, unlike the bite taken out for a partial, is basically you'll see at totality, you'll see the moon, and you'll see just kind of a ring. So annular is sometimes called a ring at totality. So those are the types of eclipses. Okay? All right. On to chapter 3. Dun, dun, dun. And I told you of all of those kind of cool little things, I picked this one, the sun dagger. So the sun dagger happens to be special at noon on the summer solstice. And I told you just a little bit ago that this one will also be on the test, that Eratosthenes was able to estimate the circumference of the Earth based upon kind of shadows that was projected at the same time from one location, or the distance between those two locations. Ptolemy, remember the P is silent, Ptolemy violated the keep it simple, stupid law, and he came up with this use of epicycles, where the planets do loop-de-loos to explain the backward, the retrograde rotation. So there's a figure from your textbook of Ptolemy's introducing epicycles. Apparent retrograde motion of the planets. Here's where I bring in the figure from your textbook, actually from the end of chapter 2, where this is actually showing you the blue is Earth's orbit and the orange is Mars' orbit, and when Earth overtakes Mars, that's when Mars appears to go backwards. Major contributions of Copernicus, Brahe, Kepler, and Galileo. Seems like we just did this. So as they're written, they're kind of in order. So Copernicus had a student Brahe, Brahe had a student Kepler, and Galileo kind of came up with some important things. So on my review page, what I did was I said Copernicus sun-centered model, Brahe was his observation, Kepler was the 3 laws of motion, and I kind of brought those in from the slide. Galileo, see below. Actually, Galileo is the last bullet on this. Kepler's 3 laws of planetary motion. I don't think I have anything. I just kind of left it with what I had before. Perihelion, aphelion, and this was one that Nellie asked about. Just kind of know them both. Peri kind of thinks of close, like you're parrying with someone like on guard, you know. And aphelion is farther, just like perigee is close between the moon and the Earth, and apogee is far. Okay, so Occam's razor is the keep it simple, stupid principle.
I didn't know what that meant.
Yep, keep it simple, stupid principle. Don't make it complicated. So, and actually that is a hallmark of a good, solid hypothesis or theory. Hypothesis, like I saw it said on the previous slide, is a proposed explanation based upon observations. And then the last one, which seems like we just talked about this, okay? Galileo did many things to reinforce the sun-centered model, including the sunspots and craters on the moon. Thought the whole heavens must be perfect. Moons orbiting Jupiter. That was helpful to see that some object can have satellites like that. Phases of Jupiter, Venus. The distant stars in the Milky Way said, well, that's why you don't see parallax, because they're so far away. Okay. Any questions? So like I said, I will add those. Okay?